Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody watching us from the future. So today we are going to continue and finish the lecture on querying trees, which will complete a very big part of the semester that was dedicated to data shaped as trees after the tables. And then we'll start with graphs, which is the third data shape. And then next week, we'll look at cubes, which is the fourth data shape. The fifth one, we saw it in information retrieval, vectors, and you'll see it also in large language models if you're interested. But we did see a few vectors today, but I'm not saying much more than that. So yes, let's take it from where we were. So I explained last time, so I showed you the query language and everything that works like a Lego game. And then we were talking about the implementation of that query language, because you can make it work on top of MongoDB, on top of Spark, on top of any host language implemented in Java, in C++, on the local machine, on a cluster. It's just a query language, just like SQL. SQL you can also run on top of anything, and that is data independence. Now, the way that RumbleDB was implemented is that on the physical layer, it uses many different ways to run JSONic. It's able to run it locally on the machine in pure Java code. It's able to run it on top of Spark RDDs. It's able to run it on top of Spark data frames, transformations. In some cases, it's even able to run it purely natively in Spark SQL. What I mean by that is that typically when you have an RDD transformation, you remember that in filter, map, and so on, you have a lambda, right? You have to provide a function. Normally, the function that is provided is just a Java code black box that is the RumbleDB code. So you take all the codes that you need to run in parallel on the machines, pass to filter or map and so on. So it's shipped as what's called a UDF, a user-defined functions. But it's slow because you still have to execute Java codes within the Spark transformations. Native Spark SQL means that there's not even any function or UDF to pass as a lambda. It is purely Spark SQL. You're able to translate literally JSONic to SQL in some cases. But anyway, it's able to switch seamlessly depending and adapting to the query between one or the other. I already told you that in the very simple cases where you have very simple queries like this, it's entirely local. If you have some expression that you know will only give you one item, it's a simple method call to get it in the API. If you have potentially more than a few items, but it's not worth parallelizing, then it's going to be over a Volcano iterator pattern, meaning next has next, next has next, and so on, streaming through them. There's also convenience methods to materialize. If you don't want to go and bother with next has next, next has next, you can directly ask for everything as a single list. That can also be done. But this is the local. And I also, at the end of last week's lecture, I told you what happens if RumbleDB detects that it can do it in parallel. How does it detect it? Well, for example, you use the function JSON file that reads .jsonl, it's a JSON lines file from HDFS. So imagine that here, by default, the file system is set to HDFS and we are in the same directory. We just say a JSON file, persons just .jsonl. So here, it knows that it can open it as an RDD because it could be not valid JSON, right? Could be a huge mess with plenty of objects that don't look like each other, which is the case here. And then it's going to turn it into an RDD, right? So you can imagine what's happening below the scenes. Below the scenes, it's going to ask Spark to open it as a text file, and then it's going to use parse.json, some JSON parser to open each line independently as an object item, and then you get an RDD of items, okay? Then what happens is that all the expressions, and I showed you that last week too, are called with a Spark transformation. So you can imagine the navigation, when you look up and go one level down, then you can use an RDD map, flat map actually, and you pass the UDF, and the UDF is what has the code to take a JSON object and extract countries from it, right? That would be the UDF that you pass. Then you can do the unboxing again with a UDF, and then you again have the Java code that is able to convert an array to a sequence of items, right? When you open an array, then you have again these distinct values. That's again a transformation is going to use distinct, right? So you see it translates everything to Spark transformations. Who is with me? Right? So this I showed you last week. But here's the thing. In the case of opening a JSON lines file, I don't know if there's a schema. Could be a huge mess in the file. But there are cases where I'm opening a data set and I already know that there is a schema, I even know the schema. I can directly look on the disk in the header of the file and even see the schema at compile time. So in that case, instead of creating an RDD physically, I'm going to create a data frame. The user will not even see any difference. For the user, it's still a sequence of objects. It doesn't matter if it's an RDD or a data frame below. But the user will spot something. The user will see that things are faster. And they are faster because the data frame is faster than an RDD. But apart from the speed, the user will not notice the difference. Right? It's still JSONic and sequences of objects. So in that case, we open a Parquet file. In the case of Parquet, we can extract a data frame, and that's physically what we will have inside RumbleDB. Externally, it's a sequence of objects. So the idea you understood now is that if I open a data set that is heterogeneous, that can be a huge mess, I'm going to use RDDs. RDDs of items, and item is polymorphic. If you heard that from object-oriented programming, items can be atomic items, object items, and so on. It's just object orientation polymorphism, an RDD of items. If it's homogeneous, however, and I have a schema, and I know the schema is well-behaved, it doesn't have any abstract types, it doesn't have any open object types, you know, that kind of things, doesn't have any variants, then I can just store it as a data frame. Again, that's the physical implementation. It's very important. That's physical. That's completely hidden from the user. Who is with me on that? Right? Okay, very good. So RDDs when it's messy and heterogeneous, and data frames when it's homogeneous. But data frames are also used for something else. They are not only used for sequences of objects that have a schema, that works very well with that. They are also used for the implementation of flower expressions, more exactly for individual flower clauses, for, let, where, return, group by, order by, count, and so on. You remember flower? I told you it's at the core of JSONic, XQuery, and many of the other 3 languages. It can do everything SQL can do, like select from where, but I explained last week it's more flexible because we have a model that just changes the clauses in any way you want. And so you remember last week I showed you that the way the clauses work is that they pass tuple streams to each other. Do you remember this? Who remembers that? Right? I showed plenty of examples. And again, you might remember, why not sequences of items? Because I said everything is a sequence of items. But the clauses are not expressions, they're clauses. Only the flower expression as a whole is an expression. So the return clause at the end will return a sequence of items. But in between the clauses, these are not expressions, these are clauses. And so they return tuple streams. And we saw that the tuple streams, in fact, can be seen as data frames. It's highly structured. Why is it structured? Because every column in the data frame corresponds to a variable. And the variables, they are not at compile time. You cannot have any dynamic variables. They're all static, they're all known, they're all in the code, basically. So concretely, imagine that we have this JSON file that we open. It's messy. So do I use a data frame or an RDD? Okay, let's vote. Who says an RDD? Who says a data frame? Okay, we have a majority of RDDs, so it's democratic, it's Switzerland. We decided it's an RDD, right? You're following, that's great. So it's an RDD because it's messy. We could not fit that in a data frame. You see, because of this, see the name, it's a string, it's an object, and so on. And so if you open a JSON lines file, you cannot know in advance. So we know an RDD. Now what we do, the moment we put that in a for loop, in a for clause, what happens is that we have one variable, so that's going to create a physical data frame with one column for that variable. So in that case, the variable name is person. So I'm creating a data frame with person, right? Now, there is a trick. That's a physical implementation detail. Because this is heterogeneous. But the thing is, anything in Java, you might have heard of Java I/O serializable or of CRIO. Whoever heard of these things? So who heard of Java I/O serializable? Right? It allows you to serialize with the native Java way. And the other one is CRIO. Who heard of CRIO? Maybe I'm saying it with a French accent. Who heard of CRIO? No, you didn't. It's an even better way to serialize Java objects to sequences of bytes, even faster. So basically, the Java objects that we have, in particular the items, we are able to just serialize them to sequences of bytes. And what I store in there in my data frame, the type of that column is actually sequence of bytes. This here is all serialized to bytes. Okay, who is with me? Right. So this is how we fit something heterogeneous because it's polymorphic and all serialized as bytes. And of course, whenever we read it, we deserialize. There's a few caching and things to accelerate things a little bit, but this is the idea. Then comes another clause. So that's this tuple stream that we model as a physical data frame comes out of the for clause. Then we have another clause that is another for clause, so that adds a second column, right? That's how the tuple stream evolves. Now we have two variables that are binds. So we have person and country. You see that here we call flatten. Flatten is just extracting the content of that and flattening it, just in case there might be even nested countries. Maybe it's an overkill, but anyway, we just flatten everything, get a list of countries. In fact, it's similar to the explode and the lateral views. Who remembers the lateral views? Right? Here we don't need any lateral view, we just add another 4. It's exactly the same logic. But anyway, you see that since we iterate, now we are going to have one binding for every one of the values, and the first variable still remains the same within each window here. This is done with Spark SQL plus UDFs. What do we have in the UDF, in the user-defined function? We have the runtime iterator that corresponds to this. We just turn that and wrap it inside the lambda, inside the function. It's purely Java code. And then we ship it as a user-defined function in the SQL language, because we can create new functions in Spark SQL and bind them in this way. And then we have a Spark SQL query that uses lateral views and explodes, but you don't see it because it's taken care of internally, and gets this out. Who is still with me? Right? Very good. So you see the user writes this, and internally this happens. Then we have a where clause. The where clause is also entirely written in Spark SQL internally. What happens is that this here, whatever is in here, that's a runtime iterator, is again put inside a UDF that is exposed to Spark SQL. And then in Spark SQL, we write some code that uses, guess what, a where clause, a Spark SQL where clause, where in the where clause, we call the predicates that contains the runtime iterator for the predicate in JSONic. You see how it's just taken over to Java. And then we get a data frame physically that just has less records. Who is still with me? Right, very good. See, we filtered for country equals US, and as expected, we have country equals US. Then I have a let clause that adds a colon. It just declares a variable, so that adds a third colon in there. And again, the same, we package that into a lambda, into a UDF, we expose it to Spark SQL, and then we create this. As you can imagine, what's going to be here in SQL is in the projection, in the select clause, we are going to do select person, country, and blah, blah, blah as first name, where the blah, blah, blah is the function call to the UDF that wraps the runtime iterator that corresponds to this, oh, that's a mistake. That should be colon equal, of course. That corresponds to this, right? It should be colon equals right there. You will have corrected it. Who is still with me? Right? So the let clause adds another colon. And again, we did it with Spark SQL. Return. OK, now it's the end of the flower expression. We are returning to the light side of the force with the sequences of items. And now we get out of that, again, an RDD, right? So we are going to, again, have some sort of flat map that generates all the items generated by the return clause. And then I end up with maybe, let's say, some data frame that has the serialized as bytes, that has the item serialized as bytes. And I can write some Java code that just decodes it and turns it into an RDD of items again. right? And then I have the results like this. In that case, it's an RDD of strings and string items that is going to be returned. Who is with me? Right, very good. So you see, it shouldn't surprise you because it's not the first time you see these animations of flower, but basically we literally use physical data frames to execute all of that. And now you see why we are capable of supporting these very generic queries, even though Spark SQL does not support that, because we just compile it in such a way that it just works. And again, all of this complexity here, the user doesn't even need to worry about these things. It's the data engineers that implemented RumbleDB, aka the students who took the class previously, who took care of all this hard work so that nobody else has to do it ever again. That's the idea. Okay, so we are there. And to summarize, in the case that we have something parallel, we use data frames. And then in the case that we do something super simple that doesn't even have anything parallel in there, we take care of these tuple streams locally. Then we don't even bother to do data frames. We have a Java class called flower tuple that has one line, basically, and we just use next has next and so on, but we use next has next on flower tuples instead of doing it on items, as we were doing with the expressions. Who is still with me? Right? Very good. So this is the way it works. So that's for the flower clauses. And again, a recap for the expressions. That's what I explained last week. We have the execution where we know it's a single item statically at compile time. We can already say at compile time it's a plus, so we know it's at most one item. Direct Java method call in RumbleDB. Here we know it's local, it's small enough that it doesn't deserve parallelism. Simple iteration, next has next. Messy data in parallel with RDD transformations. Structured data with a schema that we can read statically from Parquet. And then we get data frames transformation. And then with queries that are so simple that this can directly be written as SQL, then I do not need to create a Lambda and a UDF. I can directly write in SQL foo plus one, right? So this is what I call native SQL. This is going to be natively executed as Spark SQL. So you see plenty of execution modes, and RumbleDB is going to figure out whatever the fastest way is in a way the user doesn't even notice, except that it's faster. So these are the expressions. Now, the internal architecture of RumbleDB is quite simple. I told you last week, we basically parse the query, then we create a static context that we fill with all kinds of statically detected types. So it detects the types statically. It tries to infer the types statically. What is the benefit of inferring the type statically? Well, if we know that some variable has a type that has at most one item, and not more than that, then we know we don't need Spark. We know we can do a simple method call. So there's a lot of benefits in the compile time analysis. So we infer the types at compile time. By the way, when we do that, we are allowed to peek into the Parquet file, right? If the name of the file is a simple string that I can already read at compile time, then I allow myself to read the header of the Parquet file and get the schema, and then I can derive all of the types. Once I have that, I can determine the execution modes. I can see the parts that might have a lot of items, then I do RDD data frames. The small ones, at most one item, I do locally, and so on. And I label every single iterator, every single runtime iterator, with an intentional execution mode. I intend to do this one locally. I intend to do this one as a data frame, and so on. And then we have the runtime iterator tree, and we just pull the items from it. Okay, so that's a very classical architecture, and it shows the utility of compile time optimizations to run things smoothly. That's an example of what's happening. So we have a query here on the top left, which is a bunch of clauses. You see here the streams of tuples. We have the return clause, the where clause, the for clause, return where for. So we have streams of tuples here as data frames, right? Because it knows that it's read from HDFS or S3 or whatever the default file system is. Here, that's just a method call because it's just a string, so it gets the string. Here, it's messy, so we use an RDD. Here, it's just local stuff, so it's just a Volcano iterator, next has next, these two. Here, it's inside the where clause, so we wrap that into a Lambda, into an RDF. So all of this runtime iterator is wrapped into a Lambda and shipped over to Spark with a Spark SQL query that does a where, right? And this here also, that's local, that's a method call, that's a method call. So you see here, coming from the left is a data frame. So we also wrap that into a UDF, into a user-defined function, a Lambda that we use together with Spark SQL to then produce an RDD that has the sequence of items. And then that sequence of items can be printed to your screen, can be written to disk, and so on. For whom is that clear? For whom does that make sense? Right? This is all taken care of by RumbleDB. We have a raised hand. Yes? Maybe small hops too. Yeah. You need to be very careful with the microphone. Yeah.
Yeah, you just said that when a query is very simple, it can get converted into like it executes in place in the form of SQL. So is it like a subtree in this particular tree? If that is very simple, that can also be executed as a SQL, and then how does it integrate? Or is it like a complete tree if it's very simple?
Yep, you're absolutely correct. So maybe you're referring to this. So when you have something that is simple enough, it's not going to create a Lambda and a user-defined function. This will directly result in SQL codes. This will directly be written in SQL. But you might have a super complex query of 10 lines with plenty of elaborate things. In that case, it's just simpler to just ship it as a UDF. What's going to happen when you create a UDF like that is that the UDF will be broadcast to all the machines in the cluster, and the UDF will be called locally on every one of the Spark machines. Okay. So imagine you have a where clause that calls the UDF, right? What happens is that it's distributed over the machines. So what happens is you have the partitions of the data frame before the where clause. It's partitioned over the cluster. And locally, every machine, every executor in Spark will have tasks. And the tasks consists of filtering the data frame because of the Spark SQL where clause, calling the UDF for every single record in your data frame. But this is done in a distributed way. And again, it's magic because it's done by Spark. In RumbleDB, we did not even bother with that. We just wrote the Spark SQL where clause that calls the UDF. All the rest is handled by Spark.
Okay, so every sort of like at every materialization node, we check that whether the query that is coming from one of the subtrees can be transposed like as a SQL itself or like as a UDF.
Exactly. There is some code. It's basically trying, right? It attempts to compile it to SQL. If it succeeds, it goes ahead.
Okay.
If it doesn't manage to compile it to Spark SQL, it falls back to the UDF, where you serialize the runtime iterator and ship it to the cluster, right? But you can imagine how costly it is because you really need to serialize the runtime iterator, and I mean here again with Java.io serializable, right? So you use that to serialize the runtime iterator as a sequence of bytes, and then that is shipped to every machine in the cluster so that it can deserialize it and call it as a Spark function, as a SQL function. Right. Okay. All right. Who has read the Rumble paper? Right. So I recommend you read it. There is a link normally in the course material, and it's all explained in there with a few examples of how it's done. Right. So basically, this is it. And again, all of that hard work is completely hidden from the user. People do not even need to worry about these things. This was just done once and shipped as RumbleDB, and then people can just use it. Here's another example of how it works. You see, I have a very simple query, but working on petabytes of data. That's messy, so we open it with an RDD, right? Because it's messy. Otherwise, if Parquet, it would have been a data frame. RDD transformation with a UDF. RDD transformation with a UDF, flat map, flat map, flat map again, flat map. Then I get an RDD. The sum, you can do that with a Spark reduce, right? You can just put the addition and use the Spark reduce action, and then you get a single value. Right? And then again, that's a simple method call to extract it at the end. Who is with me? Right? So you can see here how the user just writes the query language, and all the rest, the purple rectangles, it's all hidden from the user. So you're sitting on your Jupyter notebook connected to the cluster, you press return, and you get the results very rapidly, and in the background, there were 1,000 machines that took care of the execution. Right? That's the idea. Okay, so the big picture that we have here is again that we have a data lake, but in fact more like a data lake house that has updates, that has machine learning, that can do data warehousing. We're going to talk about data cubes and data warehousing in 2 weeks. So this is the idea, and this is the evolution right now. I would say it started in 21 with the Lakehouse paper published at the CIDR conference, so 4 years ago. And now the entire industry is moving from the data warehouses and the data lakes to the data lake houses where you have everything integrated. So the future of big data is the data lake houses that are analytical, operational, so it's OLAP and OLTP. In fact, there is even a keyword from that. I think it's called HTAP, I think, hybrid transactional and analytical processing. That is basically the future, where things are now going, and we are going to have ACID guarantees at the level of the entire cluster, hopefully in the coming years. Everybody's trying to do that. Right. Oh, wow, that was the slide where I had the data warehouse on the left and the data lake on the right. This is what I mean with the future, where you have the data lake house, and you see it has everything. You have the data lake, but you have the BI, so the data cubes, you can do data science, machine learning, and here you have all kinds of fancy implementations that index your data, that allow you to update and so on. That's the data lake house. Remember that word, data lake house, because this is going to probably stay. By the way, if you're interested, this is the CIDR paper, if anybody wants to read it. You see the people, you know the names, right? Ali Gotzi, so they are all the executives of Databricks. Okay. I just have a few more slides, but this is just to show you an example of cleanup. So again, the idea of the data lakehouse is that you have messy data. You need to fit it into a machine learning process. And here I really mean a classical one, not ChatGPT. So a classical one would expect structured data with features and with labels. So you can clean up your data using some JSONic code that works on messy data, then you can validate it, then you can save it in a structured format like CSV, Parquet, and so on. And then you can, so that's also another example of things that we clean up, right? That's yet another example. I'm not going to stay in that. You can look at it offline. That's just to show how you can use JSONic to clean things up, right? You can, for example, go over the fields that are heterogeneous, and then depending on the type, you convert them to something that is more homogeneous. The same here with the countries. If it's a string, we put it in an array. If it was null, we put an empty array. And otherwise, we just take it because it was an array. And you see now at the output, you always have an array, right? So this is how you clean it up, right? For whom does that make sense? Right? So we use that to clean up. And then, and again, that's absolutely not part of the material, but there was a beautiful master thesis written now a few years back that exposed machine learning models as JSONic function items. And you can also do machine learning in JSONic in this way and train linear regression, everything. In fact, what's happening below the scene is SparkML. It's all shipping everything to SparkML. Okay, so now I want to make sure that you more or less followed what I've been saying. So a lot of what I presented is actually the work of your predecessors, so the students who worked on this in the previous years, and maybe some of you will take it from there. Does it actually work? Yes, it does. Okay. So again, anything that is not clear, you can send us emails, you can write on the forum. And again, for the use at the exam of JSONic, so it's good to know what's inside, but on the exam, you just write JSONic. That's the idea. Okay, that was a bit trickier, but of course there was a lot of work that went into writing this. Right, it's inside. It's actually quite complex. Okay, so more on the less than 50. Maybe it's also due to the fact, as I told you, that it's the first year that I do the lecture in this way. In the previous years, I was just basically giving the JSONic tutorial over 3 hours. And then I changed it in this way, offloading the tutorial to the Jupyter notebooks and focusing more on the implementation. And so, of course, the effect might be that I focused on the more complicated things in this lecture. All right. Oh, somebody understood everything. Very, very good. Okay. All right. Very good. And again, everybody, less than half, less than 50%, send us emails, ask your TA in the exercise session. You can send me directly emails also. It's totally fine. And again, as I recommend, read the paper, the one that's called the Rumble Data Independence for Large Messy Data Sets. Okay. So are there any questions? Actually, you can even ask questions now. Don't seem to have questions in the lecture hall. What about Zoom? No questions. Oh, wow. Okay. Yeah, yes, a question there. Okay. Let's gently pass over the microphone.
What's the name?
Yeah, there you go.
But that's more organizational, because you mentioned on Moodle that the textbook, this chapter is still being developed. So.
Oh, the graph databases.
Yes.
Yes.
Yes. So when we expect to have a chapter?
I intend, so it's under time constraints. I would like to find time to continue it. I hope in the week. But in the worst case, you anyway have my slides and the lecture and everything, right? Because the textbook is basically a written version of what I'm saying in the lecture. I do have the intent. That's what I told myself that I need to at some point. That's the intent to finish it. Actually, I think it's the last missing piece of the book. So then the book would be complete. Maybe also the conclusion. Yeah, but thank you for asking, and thank you for pushing me, because it does motivate me to continue and finish that chapter too. Okay, that's a chapter about what I'm about to tell you about right now. Okay, very good. Thank you. Yes, another question over there.
Yeah. Thank you. Given that Rumble is our JSON is its own language, do you also support kind of the more advanced features we've seen before, like indexing or authorization?
Jein. The Jein is just for ja and nein in German. Is when you want to say yes, a superposition of yes and no. The idea is that it can support indices because it's a language just like SQL. It's just that since we use Spark mainly at the moment and Spark doesn't have indices, then there's no indices, so it would just scan. However, when you add, for example, PostgreSQL and so on, at the time it's done with a Spark connector. So it would just take the entire data set out of PostgreSQL or out of MongoDB and then deal with it with Spark. However, I could present it as future work, even though it's actually already been done in the past. You can also re-implement the part of RumbleDB that connects to MongoDB or to PostgreSQL to compile it to SQL or to the MongoDB API instead of the Spark connector. Then you would directly benefit from the indices that MongoDB can build and from the indices that PostgreSQL can build. Right?
Okay, but you don't plan to do features like that within the language itself. So you'd have to configure the runtime where you're using JSONic in to build the index beforehand.
I see where you're going. So you mean to extend the language with index construction?
Yes.
It's already been done. It's already been done. I don't know if it's online or if it can be found online, but I have colleagues that designed an extension, actually not of JSONic, but of XQuery, but it's the same, that provides functions that are actually side effecting the functions, but there is also an extension of JSONic that has side effects. And that gives you a whole library to build your indices in this way. So it exists. It has also been implemented. The engine actually is called Zorba. It was co-developed with Oracle and many other participants. It's just that it's no longer maintained. So there is, it was there for a while, but now there's been so many operating system updates and of Ubuntu and so on that I don't think it would still work. But it has been done, so it shows that it's doable. If at some point we have resources or there is an interest, we could also again set up a project that somebody re-implements it. And basically what you would do then with something like this is that you could use HBase, for example, to store the index, right? You could build the index and then store it in HBase, knowing that you use the row IDs for a hash of whatever you're indexing. And so I think it would work very nicely in a distributed way, right? But it might be that we don't even need to worry about it, because it could be that at some point, the people who design the lake houses, that data lake and so on, maybe at some point they will provide indices. And then we will not have to do it. Or at least we will just say, oh, you want indices? We just forward the instruction to create them to the Delta Lake, and then it takes care of it for us. Mm-hmm. Right? It's really the idea of it's modular, so you just have a layer in between, right? Okay. It's also very new, all of these things, right? So,
thank you.
Thank you. All right. Any other questions? Right. Okay. So I'm going to move on to the graphs then.